Yes, please. My talk will range over many topics, some of which I don't know very much about. But please stop me at any time, and I'll try to explain more. It's based on these two papers. The first one was a collaboration with many people. The second one, I'll say, is a collaboration just with Fernando Brandão. And the first one is also with Fernando, as well as Boaz Barak, John Kellner, David Sturr, and Yuan Zhu. So in this talk, I want to tell you about, let me give you the rough outline. The rough outline is I'm going to tell you about connections between different problems. I guess I'll have to define also the problems. And these are computational problems. So then when we connect problems, one thing we want to get out of this is hardness results. So I'll tell you about some of those. Another thing we can get out of it are algorithms. If you have an algorithm for one, translate it to the other one. And then I'll talk a little bit about open questions and sort of what I think some of the prospects are for the line of research I'll tell you about. So let me first tell you about sort of the cast of characters, the type of problems we'd like to solve. So the way I see it, there's sort of a range of problems. And maybe on this end will be sort of more classical. And as I walk towards that end of the board, it'll become maybe more combinatorial here, classical computer science, and towards the other end, more analytical, more quantum. And I'll explain the connections between them. So one of the first motivations for this is the unique games problem, which I imagine many of you have seen before. If you haven't, then a sort of representative example of it is given a system of equations of this form, how many of them are solvable? So if they're all solvable, to determine if you can solve all of these equations simultaneously or not is easy because it's linear algebra over a finite field. But if you want to ask, is it greater than 1 minus epsilon or less than or equal to epsilon satisfiable? In other words, does there exist a set of x's that will satisfy a more than 1 minus epsilon fraction of the constraints? Or does any choice of x's satisfy at most an epsilon fraction? This we don't know the difficulty of. And this is sort of, you can think of this as roughly the unique games problem. And in this work, so I'll talk about connecting this to more analytic problems. And the first connection was something that I didn't do. This was work by Raghavendra and Sturr, I believe, where this was connected to the small set expansion problem. So in this problem, we have a graph, and the expansion problem is to measure what is the least expanding set of no more than half of the vertices in the graph. And small set expansion is similar, except instead of looking at sets that can be up to half the vertices in the graph, you look at sets of size up to, say, 0.01% of the vertices. So to make that more precise, let's say you have a regular graph, and you define the measure of a set of vertices to be this normalized quantity here. And the expansion profile is, so the expansion of a set is the probability, if you draw a random edge, that given one endpoint is in the set, what is the probability the other endpoint is outside of it? So this number is between 0 and 1. And small set expansion, actually I'll define one more thing, which is phi sub delta is the minimum phi of S over all sets S of size less than delta. So over all sets of, say, no more than a delta fraction of the vertices, what is the least expanding of those sets? And the small set expansion problem asks whether this quantity is large or small, to estimate this quantity. And just like in the unique games case, we need to estimate it only very crudely. So we'd like to know if this is greater than or equal to 1 minus epsilon or less than or equal to epsilon. And there's a sense which I want to be a little bit vague about in which this is equivalent to unique games. It's not exactly equivalent, but it's, there are reductions in both directions. In one case to unique games, and in the other case from something pretty similar to unique games. To unique games on graphs that themselves have small set expansion. OK, so I want to talk about how to look at these problems using more analytic techniques. And so the first step towards doing that will be to talk about them in terms of a matrix norm. So I've defined two problems so far, and I've asserted that they're equivalent. And the next problem, which I'll give you a little more justification for why they're equivalent, is the 2 to 4 norm of the matrix. So define the p norm of a vector to be the pth root of the average of the pth power of the entries. So we're using the expectation over the entries instead of the sum. And we are, so the usual Euclidean norm would be that when p is equal to 2. And as you increase p, it weights more strongly the heavy elements of the vector. And the 2 to 4 norm of a matrix you can think of a matrix norm in terms of how much does it blow up the norm of an input vector. How much greater is the norm of ax than the norm of the input x. And it's 2 to 4 means that we measure the input and output norms differently. The input norm is still measured in the usual 2 norm, and the output norm is measured in the 4 norm. And so it's like, at what rate can you convert US dollars to euros or something like that? And one way to think about this difference between the 2 and the 4 norm, I think it's already interesting to think about the identity matrix. What is the 2 to 4 norm of the identity matrix? And so this, for the n by n identity matrix, the 2 to 4 norm is, I always get this should be n. All right, let's try and, I get confused because I go back and forth between using the expectation and the sum norm. So let's think about this. So the 4 norm, you would like vectors to be concentrated, and the 4 norm is highest. So if you have a vector which is a 1 followed by all zeros, then the 2 norm will be n to the minus 1/2, and the 4 norm will be n to the minus 1/4. So then this thing right here will be n to the minus 1/4. What's that? Minus. If it's minus, no, it's n to the minus 1/4 divided by n to the minus 1/2 equals n to the 1/4. Yeah, good. And so what does that reflect? This is the most that the 4 norm can be larger than the 2 norm. The biggest gap between them occurs for these very concentrated vectors. Whereas if you put in the vector of all 1s, the 2 norm and the 4 norm are the same. And the reason I always get confused is if you put in the sum norm, those two things are reversed. Good. So this is the most, if you have a matrix which preserves the 2 norm, a unitary matrix, then this is the most the 2 to 4 norm can be is larger by this factor of n to the 1/4. On the other hand, if you have a matrix of let's say a matrix where all the entries are 1 over n, then the 2 to 4 norm will be 1, because whatever you put in is going to map to something of this form, and so you can never have something whose output is bigger, has a bigger 4 norm than its 2 norm, and also this thing is contractive in 2 norm. So intuitively, if you now apply this to the adjacency matrix of a graph, this tells you something about the graph. So before we get to 2 to 4 norm, if you just look at the regular 2 to 2 norm of an adjacency matrix of a graph, let's say the normalized adjacency matrix, so it's like a random walk matrix. Well, this quantity is always 1, so that's not very helpful. But if you remove the top eigenvalue, then that tells you something. It tells you the second largest eigenvalue, and it tells you about expansion. And the reason for that is that it tells you about the rate at which a random walk mixes. It says when you remove the top eigenvector, it tells you about if I'm orthogonal to the stationary distribution, how quickly will that vector decay under mixing on the graph. And that in turn tells me about expansion. If I take the 2 to 4 norm, then that is in some way similar. It tells me about how sets expand, except the 4 favors small sets. And so it won't tell me just about expansion, but it'll tell me about small set expansion. And this...
There's nothing particular in the 4, anything bigger.
That's right.
Than 2
That's right. That's right.
Just convenient.
That's right. And so the particular theorem that makes that precise is that if A is the normalized adjacency matrix of a graph, and P greater than or equal to lambda is the projector onto the greater than or equal to lambda eigenspace, then, actually I'll do it this way, then the graph has very good small set expansion. So all sets of size delta expand a ton if and only if this projector has small 2 to 4 norm. So small meaning that every vector in its support has 4 norm not much bigger than its 2 norm, meaning that that it's pretty spread out. So this is less than or equal to 1 over delta to the order 1. And if you replaced 4 with some other constant, then these constants would also change. Question?
Lambda is the second eigenvalue, or is it? No.
Whatever you like.
Any eigenvalue.
Whatever lambda is, that tells you what this P is. So
You remove or you focus on the largest eigenvalue, whatever largest. As many as you like.
So yeah, so one way to think about it is that you sort of treat them, above lambda. Yeah, you can threshold it wherever you like, and it tells you basically, it corresponds to the epsilon in the small set expansion, sort of how precisely can we determine the small set expansion relates to at what level do we start throwing away eigenvalues.
Second eigenvalue has a very high multiplicity.
Yeah. OK, so this is a little bit more more analytic, and from here, OK, so now we want to ask about how can we solve this problem? How can we compute the 2 to 4 norm? And one way to do it, so let's take the 4th power. And then what is this? This is the maximum over unit vectors of the sum over, sorry, the expectation over I of the inner product of ai and x to the 4th if the ai's are the rows of A. And this we can think of as a degree 4 polynomial in the entries of x. One way to write this is to say maximum over x, the inner product between two vectors of length n to the 4. So by x tensor 4, what I mean is a vector of length n to the 4 with entries, shall call it, let's call this J1, J2, J3, J4. Entries that are just the products of the individual ones. So this lets us separate it into something that depends on the problem and something that we want to maximize over. And so now we can do things like take the convex hull of these and sort of separate it into the part that's instance dependent and the part that's universal. And now this might not appear very nice, but the idea of restricting our attention to tensor products of vectors is something that comes up a lot in quantum information theory. So I guess this is sort of the point at which I started to walk into the collaboration. Is I guess there's a third paper as well. OK, so let me tell you about these papers. This first paper so far, this theorem there about the 2 to 4 norm relating to small set expansion is in that top paper up there. I began looking at the connection of tensor optimization to quantum information in this paper, and this is where the hardness result is proved, which I'll tell you about in a minute. So to tell you about the connection to quantum information, I'll tell you just a little bit about what quantum mechanics says about the state of a system. And what it says is that the state of the system is something analogous to a probability distribution, but normalized in the L2 sense. So a quantum state is described by a unit vector in a complex unit vector. And here I would normally use the sum inner product, but I think it won't really matter for what I'm saying. And if you have two quantum systems, one with state x and the other with state y, then the joint state is something called a product state. And it's a tensor product of the two individual states. And it's exactly like if you have two probability distributions that are independent and you want to talk about the joint distribution, then that is the vector that you get. And of course, not all vectors can be written like that. And so we say that a state is entangled. Let's say a state z is entangled if we cannot write it in that form for any choice of x and y. So when you hear about quantum algorithms, people usually talk about quantum states as vectors, just as I have done. But in quantum information, people usually talk about them as matrices. And let me try and explain why that's true. This picture there's two flaws with it. The first is that these are analogous to probability distributions, but it's not obvious how you merge this description with probability. For example, suppose with probability 1/3 I have one state, and with probability 2/3 I have another state. Then, in general, what does that picture look like? Does it look like a probability distribution over unit vectors? That sounds kind of horrifying. Now we have an infinite number of degrees of freedom. The other issue with it is that the observables turn out to be are not linear in X. So an observable in quantum mechanics is a matrix M, and if we were to measure this observable, then you can think of this as something like measuring magnetic field in some direction, and your apparatus spits out a number. The expectation value of that number is x star mx. So you can just think of that as an axiom of quantum mechanics. And so these are what we can actually measure. So for example, if you multiply x by an overall phase, you'll never be able to measure that because that will always cancel with the x star. And given that this is what we can actually measure, it's convenient to rewrite this as the inner product of m xx star. By inner product, I mean trace of the product. Sorry, this should be a star. I guess observables traditionally are Hermitian matrices, so that they give you real valued quantities. When you write it like this, you've separated out what you're measuring versus the quantity you're measuring versus the state that you're measuring. And so you could also interpret this as the state. And if you do, then the quantities that you measure are linear in the state. And that's nice because that's like probability theory. If I have, because I'm talking about the expected value of an observable, that should be linear. If I take a probability distribution over different states, then expectations are linear in the underlying probabilities. And so here again, we get that feature. And in particular, you can take, go ahead.
Okay, you're just visually here. So M represents an experiment?
That's right. That's right.
So and if I multiply x star by M by x, what we get the probability that the experiment is something?
Let's say that the experiment returns a real number as the answer, and that gives you the expectation value. So this is pretty abstract. So let me be more concrete. Let's talk about a single qubit. And then you have amplitudes. Let's say x0 and x1 are usually amplitudes. And if your experiment is measure and ask what is the probability that you get outcome 1, then you'll get that m is equal to 0, 0, 0, like that. And then this thing here, when you sandwich it, will be x1 absolute value squared. And you can see that I've instinctively reverted to the sum norm, because then if you put them both together, you get that x0 squared plus this should equal 1. And so it's sort of the usual absolute value square rule, where you take the amplitude and the absolute value square it to get that. But yeah, in general, this represents some kind of experiment with real valued outcomes. Good. So what people usually talk about, so these are often called pure states. And slightly more general is something called a density matrix, or a mixed state. And we can define the set of density matrices to be the convex hull of all of these things. So I take different states with some probabilities, and this represents how you combine probability theory and quantum mechanics, saying that I have a probability distribution over quantum states. And one nice thing about it is there's only n squared real degrees of freedom. I guess minus 1 because of the normalization. That's much better than an infinite number of degrees of freedom. And also, there's a nice semi-definite characterization. This is a set of matrices rho that are positive semi-definite and have trace 1. So this is a nice alternate way of looking at these things. And it also lets us distinguish, when you combine, because this picture merges quantum mechanics and probability, it lets us combine, it lets us distinguish quantum entanglement from classical correlation. So for a pure state, if you're correlated, you're entangled, full stop. But if I have two particles that are far apart, and it's the case that if I measure them in a particular direction, then my detectors either both say 0 or they both say 1. Does that mean they're entangled? Well, I don't know. Maybe they're just correlated. Maybe it's just I flip a coin and I either write down 0 on 2 pieces of paper or I write down 1 on 2 pieces of paper. How do I distinguish that from being entangled? And you need the language of density matrices to even be able to say that sort of thing. And the way you do it is you define the set of separable states to mean unentangled. And those are all convex combinations of product states. So these are all the classically correlated states. And as an example of a state that is not of this form, maybe I'll do it over here. So let's just take a pure state that's not of that form. Consider the pure state 1 over root 2, 1, 0, 0, 1. So this is like saying that there's some amplitude on the 0, 0 state, and there's some amplitude on the 1, 1 state. So these states, you can label them 0, 0, 0, 1, 1, 0, 1, 1. So that is the analog of a classical correlated distribution. So you cannot factorize it. You cannot write it as a product state. You cannot write this in the form x tensor y. So if you take the corresponding density matrix, just take the outer product of this with itself, that will be entangled. And in general, for any pure state, if the pure state is entangled, the density matrix is entangled as well. Intuitively, that's because these are extreme points. They're extreme points already in the set of density matrices, so you cannot decompose them into anything other than themselves. So since any decomposition of the matrix will be trivial, it'll just be 1 times that thing there, you'll never be able to do any kind of reshuffling to get in this form. Yeah?
It's the same as the density matrix of x tensor y.
Yes, it is. So this is equal to x tensor y star. Oh, yeah, let me say something about terminology as well. If everything's a density matrix, the subset of density matrices that are rank 1, I will call pure states. So by pure state, I mean the ones that came from just vectors. So these are things that are, even as density matrices, they're entangled. And it's anything in a sufficiently small neighborhood of this will also be entangled. But there are also things that are, where it's not so easy to tell. And in particular, density matrices have this formulation as a convex hull of a bunch of vectors, a bunch of rank 1 things. And they have this nice semi-definite characterization. Here, we'd like there to be a semi-definite characterization, but we don't know anything that's exact. So we have these two definitions here. Here we really just have this one. OK, so what is the connection to the previous problem? So this is because this is a convex set, there's a few. I guess we could do this actually for any set, but things are nice because it's a convex set. A few natural things to define on it are the support function. So the support function is the maximum inner product with anything in the set, given an input m. And the weak membership problem. So these are now. So here I've just been telling you about what quantum states are like. So what are the computational problems associated with it? One of them is, given a measurement, let's say that someone tells you, I'm going to make this measurement. You prepare me a quantum system, which is not entangled. I'm going to make this measurement, and I'm going to pay you the expected value of the outcome. So do your best. And that's what this this optimization problem is. And the closely related problem is, you've made a state in the lab, you've determined every entry of the matrix row, and you want to know, have I actually made entanglement? So have I made something that is separable or that is far from separable? For various definitions of distance. And it's sort of a base. Yeah?
The input size is the size of the matrix.
That's right.
We are working sort of with logarithmically many qubits.
That's right. That's right. And so.
And even then, the problems are.
That's right. Yeah. So you'd think I've done the hard part. I've built this apparatus. I've measured every single entry. I've already paid a price exponential in the number of qubits. Surely that should be enough. Can I solve this problem? And we don't know how to do that. And in fact, there's evidence that you can't do that. So first of all, because this is a convex set, these problems are roughly equivalent in difficulty. There's sort of mappings between them. This is sort of, the mappings are not great. They sort of break down in the limit if you're doing this with a very low precision, which I'm going to talk about a lot. These mappings start to break down. So take this with a giant grain of salt. But I think they're roughly kind of comparable. Mostly, I will focus on this problem. I think this is the one that sort of is easier to understand from a physics perspective. And I think what got people started on it. But I think this one is more useful in terms of connecting to applications. And this problem, we have a hardness result for. So it's a pretty weak hardness result. The only thing I can say in its defense is that it's the best we know, and that we have some algorithms that might match it. So the result says 3-set instance of length log squared reduces to estimating, figuring out if h sep is equal to 1 or less than or equal to half for some m satisfying that's positive semi-definite and between 0 and the identity. And the size will be like n squared by n squared. Or I guess, this should be this is order log squared n. Actually, there's tildes in there too, but it's roughly this. OK, so if I could solve this problem in polynomial time, then I could solve this problem in polynomial time. And that's not as offensive as being able to solve full 3-set in polynomial time. But if you believe the exponential time hypothesis, then that would imply this takes time n to the log n. So this would imply an n to the log n lower bound for h sep, assuming the exponential time hypothesis. So
So this is just any three set with log squared n variables?
yeah, that's right.
So you think of n as the size of the formula.
Actually, sorry, not log squared n variables, log squared n clauses.
With n variables.
No, with log squared n variables and order that many clauses. Basically, I don't want the density of clauses to be, I want each variable to participate in a constant number of clauses. I want the number of variables and clauses to be related by a constant.
That would output some generality. The general twist.
It is, but I don't want to give up even polynomial factors in the reduction, so I want to be careful about that.
3 sat is already NP complete.
What is?
3 sat is already NP complete.
3 sat.
Yes. When you have each clause including 3 variables and each variable appears 3 times in the whole formula.
That's right, but NP complete can include polynomial reductions. So I don't want to, I don't want to lose.
So why don't you say that another statement would be just that the normal three sat with a linear number of clauses
Sure.
reduces to this problem with size 2 to the root n?
That's also true. But again, I have to be careful about normal 3 sat with a linear number of clauses. Yeah.
For function that's
Yeah. I mean, I guess it's, this is the strongest version of it. So,
and there is an algorithm that's good for h sat.
so not really, but let me tell you what we have. So there's an algorithm. So actually, let me say a little bit more about this reduction. I said that we have M of this form. And actually, we have M of even slightly, we can say a little bit more about the form of M. We can say M looks like this with all of these entries positive semi-definite. Okay? And so this is like, you see, this sort of looks like being a separable density matrix, except it's the analog for measurement operators. So this is called being a separable measurement. Okay, so is that further restriction helpful? I don't know, but it's as far as we know. What do we know about algorithms?
Wait, what was that? So the hardness works for this too?
That's right. That's right. So what do we know about algorithms?
This is Hermitian.
Each of these things is Hermitian, and tensor product of Hermitian things is Hermitian, and sum of Hermitian things is Hermitian. When I write that it's PSD, I mean it's also Hermitian. So what is the algorithm we know? So by the way, this hardness result, that was in that 1001 0017 paper. That was me and Ashley Montanaro, building on work of a bunch of people. Aronson, Drucker, who's here but not today, Pfefferman, Shore, Beigi, I think. So there's an algorithm due to Brandau, Christandel, and Yard, but also in that middle paper we give a simpler version of the algorithm, which approximates h sep of M to accuracy epsilon in time exp log squared n over epsilon squared. So that's, if I just stopped now, you'd be very happy, right? Because it would match this, and everything would be wonderful. But then you have to say, if M is of this form, so far so good, and each xi is in this range, each yi is non-negative, and the sum of the yi's is at most identity. So this is a kind of wacky collection of constraints. And let me try and argue why they're physically reasonable. It's called 1 LOCC. And what it means, so people study, this grew out of the theory of entanglement. And entanglement, the whole point is that it's very hard to make, and it's very hard to do entangling operations. And once you've made it, you can measure the system, but it's really hard to interact the two for a joint measurement. It's much easier for one party to measure his side and then maybe send a message to the other party, and then she measures her side. And so such an operation is called a one-way LOCC, local operations and classical communication measurement. And that's what this is. And so these constraints here correspond, let's call the parties Alice and Bob, correspond to a measurement for Bob. And these yi's correspond to different outcomes for him. And they should each be non-negative, because the outcomes should each individually have a non-negative probability of happening. And this means that the probability should add up to no more than 1. Given outcome I, he sends message I to Alice. She makes a measurement xi, which has the usual constraints on a measurement. The probability should be between 0 and 1. So physically it makes sense, but I admit that these equations look kind of horrifying. And it's a smaller class than this one. Now, how much smaller, how close are these two to matching? Sort of up to interpretation.
Why is it smaller? M, you said, is upper bounded by I.
Yeah, but an M has this form, and it satisfies these constraints. But this,
The last one, yeah, sure.
that one is new. So is this a little detail, or is it crucial? I don't know.
The number of i's is polynomial, I guess.
Yeah, number of i's is,
So in the reduction set.
even if this were an infinite number of i's,
Yeah,
you could
always n
you could sample to get it down to n squared. Yeah, that's Alschwede Winter, I guess. Now, we arrived on these using totally different methods, right? And it just seems like too good a coincidence that they you just both converge on n to the log n. But maybe neither one is remotely optimal, and they can both be improved a lot. I don't know. I've banged my head against this for a long time. I would really love if someone had new ideas. Yeah.
But you didn't say anything about the connection between Kirchhoffs and anything H-step and
Yes. Yeah. I got distracted by questions, but I want to come back to that next.
Yeah, but let me ask about it. Can you say something about the algorithm? What does it do?
Yeah, let me. Yeah, so the algorithm is. Let me come back to that, because the connection will be quick. And let me just say, I'm actually doing this now in chronological order, because with these two things known to the quantum community, it's very natural that we would then be looking for, we have this hammer, and now we're looking for nails. And now, why does this one look like a nail? So maybe I can erase this. So this is pretty easy. Take this thing right here. So you could also write this as maximum over x inner product of as this thing. So a few things to observe. When we say x star, this is a matrix, and the entries of it are xi, xj bar, right? So it's really a lot like a tensor product, except with a complex conjugate in there. And we're maximizing over real vectors there. And even if you allow this to be complex, the max will be achieved by a real vector. So the star is really just a diversion. You can kind of just think of the star as a transpose. So doing this outer product is really just like doing a tensor product. And it's really just notation to convert from. There's just some community. In quantum we have a community of making everything like a matrix, but it's not really essential. So from here to here, I've basically only done some bookkeeping change, except I've made this complex, and I've argued that's without loss of generality because the optimum is achieved for a real vector. And then one more thing I can do, because the optimum will not change the optimum, is I can change this x to a y. And again, the optimum is achieved for x equals y. And finally, this is a linear function of this, so I can just take the convex hull. So this is just equal to h sep of this thing in here. Expectation over I, ai. So that's it. So if you can solve h sep, you can solve the 2 to 4 norm problem. So now, for hardness, you want to go in the other direction. You want to say, if I can solve 2 to 4 norm, can I solve h sep? The way I've written it, it looks like 2 to 4 norm. Yeah?
Does this already give an algorithm for a small set expansion?
Yes, but it's sort of sub-exponential, just like the existing ones.
It matches the best.
Yeah.
It matches the best, really?
I believe so. And it's
The best out of the prudent,
yeah. And that's with not. There's a few things you have to do, like you have to actually put in 2 to q here instead of 2 to 4.
Oh, you're talking about that theorem.
This bottom board, yeah.
That one.
Yeah.
I see. That's equal to this one-set expansion algorithm.
Yes. What you have to do, so suppose m is not of this form. What you have to do is you have to relate m to something of that form. You have to say, what do I multiply m by until it fits into that form? And the smaller thing I multiply it by, the worse my approximation gets. And then, so you have to kind of estimate how much do I have to multiply it by before it fits into that form? How much approximation do I give up? And if you're careful about that, then it can just match the existing small set expansion. And that is in the top paper, the one with all the Microsoft guys. So you're right. So that's one direction. For the other direction, we want hardness. And that one's less trivial because all this tells you is that 2 to 4 norm is a special case of h sep. So to go in the other direction, it takes some more effort, and it actually involves more quantum ideas. So it involves ideas.
Sorry, what's this thing again?
I want to. So I have a hardness result here for h sep, and I want to extend it to a hardness result to the 2 to 4 norm. Right?
And h sep is known to be closely connected to 2 to 4.
So I just described to you how the 2 to 4 norm is weaker than h sep. It's a special case of h sep. And it would be fully general, except not all matrices have this form. Like this perhaps looks more symmetric than a general thing. And in particular, the matrix cannot project onto an entangled state or things like that, which might make a big difference. And so h sep is at least as hard as 2 to 4. Can we go in the other direction? In other words, another way of saying that is, suppose I want to solve h sep for a general matrix M. How can I turn that matrix into one of this form? Yeah. Yeah, but also even this this tensor product, right? The most general thing would look like something of the form AI, BI transpose tensor CI, DI transpose. That's true. So the hardness, that's right. So the hardness takes us, that's true. The hardness already takes us to something of this form. So for what, you'd think it would be trivial to go from here to here. It took us a fair amount of sweat. And the proof is one that I cannot give an intuition for that doesn't use quantum information a little bit. I mean, so the proof is in the top paper there, and it's elementary. You know, the proof makes no reference to quantum mechanics, but it's the kind of thing where when I showed it to my non-quantum co-authors, they said, you know, where did you pull that out of? And when you show it to a quantum person, it's sort of natural. So I don't want to argue that quantum mechanics is essential for it, but it was necessary for our intuition for it.
But it is a reduction from this general form to the special form.
That's right. That's right. So we can say now that these are essentially equivalent. So we have a hardness result. The punchline is we have a hardness result for the 2 to 4 norm. That's the same quasi-polynomial hardness.
Does it say anything about quantum mechanics, the fact that it's equivalent?
I don't know. That's a good question. I don't know. You know, hypercontractivity, the 2 to 4 norm, I believe it was originally studied in quantum field theories in the 70s. But I don't know that literature as well as I should. It's a good question. I mean, the reduction, it's like a computational reduction. You go via things that are not very natural objects, just to show hardness. So they're not the most natural objects, but maybe if I better understood the connection of 2 to 4 norm to physical systems, then I'd be able to say more about that. OK, so then what you'd really like is hardness for small set expansion. But go ahead. Oh, yeah, right. That's what I was about to talk about. So remember, we have this chain. We have unique games, small set expansion, 2 to 4, H sep. Right? So we have this, like, sort of, you know, in each place, we're sort of building bridges in both directions. Right? So how far does this go? And now, again, we have a tragedy sort of the same form where these two don't quite match. What was the relation between these two? Well, I still have it on the board. We want to know the 2 to 4 norm of a projector onto a top eigenspace. And this construction, which I've warned you is somewhat gruesome, and I would like it if it could be simplified, but right now it's a little bit gruesome. It gives you some matrix A, and with sort of additional horribleness, you can make that matrix into a projector. But it might not be a projector onto the top eigenspace of a graph. And being a top eigenspace of a graph is a restricted thing. It's sort of not all projectors could be that. There's no way to complete it into a graph. Now, is that fundamental? Or did we just hit the limits of our ability to do algebra? I don't know. But unfortunately, basically, we do not get any hardness result for small set expansion. And it's up to you whether or not we've come close or not.
I mean, in general, some general matrix, how would you get it to be the projection of the eigenvalue?
No, that's right.
Impossible, but
Oh yeah, and you can cook up projectors that cannot be completed into. I forget how the argument goes, but yeah, certainly you can cook up projectors that cannot be the top eigenspace of a graph.
okay.
Yeah, no question about that.
Okay.
But the question is, could you make our reduction better, right? Instead of reducing it to a general projector, could you reduce it to a specific, to one that could be completed to the top eigenspace of a graph? So it would need new arguments, but maybe they exist. Yeah, so there are a number of things where it's quantitatively right. It's just qualitatively doesn't match up, and maybe it shouldn't match up. I don't know. Yeah.
What would be the result if everything matched up? What would be the best?
Right. The dream result is quasi-polynomial hardness for small set expansion. So the dream result is.
Assuming the exponential time.
Yeah. So the dream result is that 3-sat on log squared n with log squared n variables and clauses reduces to small set expansion. So that's if this reduction did what we were hoping it would do, then that's what you would get.
Can you say something about the algorithm?
Yes. OK, algorithm. So What's that?
Unless you are going to say something else.
No, that's it. So that's right. And monogamy. Monogamy is in there too. So let me. Okay, so let me tell you about. Okay, so first I'll tell you about monogamy. Monogamy says, suppose I have a density matrix on 3 systems. This subscript ABC means that this is, so here we have states of 2 systems separated with a tensor product. ABC means I have a state of 3 systems. So you can think of this as an n cubed by n cubed matrix. I mean, systems don't have to be the same size, but just think of it like that. And then you can, from this, because there's a joint state, just like for probability distributions, you can also define a marginal state, like this, the marginal state of just the AB system or just the AC system. Maybe I'll skip, well, I'll define that real quick. What that is the AB subsystem is identity on A, tensor identity on B, tensor trace on C, applied to row ABC. So this is called a partial trace. You apply the trace operator to the third system and leave the rest untouched. And a classical analog of a density matrix is a probability distribution. And if you have a diagonal density matrix, it's just a bunch of non-negative numbers that add up to 1. So that's a probability distribution. And if you do the partial trace to one of those, then you're just taking a marginal distribution. You're saying, what is my diagonal thing indexed by? It's indexed by, let's say, an A, B, and C coordinate. And the partial trace means sum over all of the C coordinates and give me something that's just a sum of a function of A and B. OK? So that's how you, if I have a 3-party quantum system, that's how I get the 2-party subsystems, the states on any 2 subsystems, or whatever. So the monogamy of entanglement property says, given such a state, then row AB and row AC cannot both be very entangled. There's a trade-off. The more entangled one of them is, the less entangled the other one can be. So this is very different than classical correlations. Classically, it could be that there's 1/2 probability that all 3 are 0 and 1/2 probability that all 3 are 1. And there's no limit to how much something can be broadcast. If someone, like if 2 parties share a random bit, who knows how many other people know it? Entanglement is not like that. The mere fact that A, B are an entangled state puts a limit on how much entanglement AC can have. And that's qualitative, but you can make it quantitative. And it's also, you can think of it as a definition of entanglement. You can say that entanglement is precisely the correlations that cannot be shared. So classical correlations can be broadcast without limit. Entanglement cannot. Let me make that a little more precise. We say that a state rho AB is k-extendable if there exists rho tilde on A, B1, B2 through Bk, such that rho AB equals rho tilde ABI for all I. So the first thing so what this says is a state could be extended to k parties if there's some other state where if you look at Alice, there are k bobs and 1 Alice. If you look at Alice with any one of the bobs, their marginal state looks the same. So one thing to observe is that separable states always are extendable. So why is that? If your separable state is sum over j, pj, xj, xj star, tensor yj, yj star, you can just take k copies of this system, and then you get a valid extension. So separable states are infinitely extendable. And it turns out that the k-extendable states form a hierarchy. So separable states, turns out, are equal to the set of infinitely extendable states. And one extendable states, that says nothing. That's just all density matrices are one extendable. And then 2 extendable is a bit of a restriction. 3 extendable restricts you more, and so on.
And we know these are proper separations.
We know that they are
Proper separations, like these are subsets of each proper subsets of each.
proper. That's right. That's right. Yes. So even for fixed finite dimension, you'll never exactly converge. Actually, one thing I'm working on now with a student is there's a different hierarchy that does exactly converge, although after a number of steps, that's sort of not very practical. But yeah, so this will never exactly converge, but it just gets better and better. So how much better does it get? OK, so it's 12:18. I don't know. Keep going. All right. So let me just briefly sketch the argument that gives you this kind of runtime. So let's suppose you have an extension from to the k copies. Then look at the mutual information between Alice and all of the Bobs.
So you are given an M and you are trying to approximate its
That's right.
maximum value.
That's right. And let's suppose that M is an even more restricted case that is even more restricted than one LHC. Suppose M can be implemented just by local measurement. And what that means is that their state becomes effectively classical. So you have your bipartite state, and you've just measured both. Every system can just be locally measured. And so when I talk about these entropies, you should think about, let's pretend for now these are just classical entropies, entropies of classical probability distributions. And to go from this to the quantum case, you just have to be really careful about how you do things. And I'll describe the basic argument and then come back to that.
So what's the input you are given?
You're given M.
You are given M, and M is of this form.
And yeah, in fact,
It's by a better form. It's just
and in fact, you're given the decomposition of M, not just M, but even you're given it in decomposed form. OK, so
M is some generalized PP outer. No, it's separable.
M is it's a separable thing. Separable, yeah. And observe that the things you get from the 2 to 4 norm are of this form. So it's doesn't inherently look terrible that you're doing it of that form, but there may be issues with the normalization that will make us not very happy. But I want to give you just a sketch of why could this work even. So look at this mutual information. On the one hand, it's at most log n, because that's the size of system A. Actually, a quantum mutual information could be as much as 2 log n, but let's just say log n. On the other hand, you can think of this as how much does Alice know about all of the Bobs? And using the chain rule, you can write this as how much does Alice know about Bob 1 plus how much does Alice know about Bob 2 given Bob 1 up to how much does Alice know about Bob k given the knowledge of all of the previous ones. So this is just an identity. There's nothing, just an equality. But already this says something very powerful, which is there are k terms here, and they add up to at most log n, so one of them must be small. So there exists j such that this conditional mutual information is at most log n over k. And now let me sketch where you get the runtime. suppose you take k to be log n over epsilon squared, the runtime, if you want to search over states of this form, is going to be like n to the k, and n to the k is going to be roughly this thing right here. So
For searching all of B1 to B2.
yeah, it's a you do a semi-definite program with that many dimensions.
But all you know is that there's one J, where there's information.
That's right. That's right.
That's now
OK, good. So I've jumped ahead a little bit. So why is this a good guarantee? Also, what does this have to do with being separable, right? This is a conditional mutual information. What does that have to do with anything? So what this says is, what this says is if I condition on these systems, B1 through Bj minus 1, these two have very little mutual information. So they're almost decoupled. And the reason I have an epsilon squared here is that when you go from the mutual information being small to the variational distance to product being small, you have to use Pinsker's inequality, you lose the square root. But anyway, just suffice to say, if the mutual information is really low, the thing is nearly decoupled. And also, recall the definition that I covered up here, that it's k-extendable if rho AB matches every pair. So Sanjeev asked, well, if I just know that for one of the pairs it matches, but I don't know which one, how does that help me? I mean, I guess you could check them all. But even before that, you're guaranteed that rho AB equals this for every pair. So if you get a bound on any one of the pairs, then that tells you something about your original state. Now, there's something that I did here that was a little bit sneaky, which is, actually, before I go on, I want to say we learned about this trick from Raghavendra and Tan, who used it a few years ago in analyzing Lasserre in sort of different setting. And it's sort of Fernando and I have used it a lot in various things. And I also have tracked me down later, and I can tell you about how to use it to find Nash equilibria. There's sort of a different, easy application of it to that as well.
But again, into the logging time.
Yes, that's right. The runtime exactly matches the Lipton-Mehta Markakis algorithm, which is not surprising, because it'd be weird to be able to do better. So I want to argue that if I condition on these things, then I get something nearly decoupled. And in order for that to make sense, I'm sort of doing a little bit of sleight of hand about whether these are quantum or classical entropies. So I'm not going to go too much into quantum information theory, but I just want to say that there's quantum analogs of all of the entropy quantities. You can talk about the entropy of a density matrix, and what that is just the entropy of the eigenvalues. You can talk about mutual information between subsystems of a density matrix, and just like you can for probability distributions, all the same ideas go through. But there's a few things that are different. And one thing that's different is that if you talk about conditional entropy or conditional mutual information, classically, you could interpret the conditional mutual information as an average of mutual informations. And quantumly, you cannot. You can define it just in terms of this entropy minus that entropy and so on, and that makes sense, but does not have that average interpretation. So one early consequence of that is that to even prove the conditional mutual information is always non-negative. This is called strong subadditivity. Classically, it's trivial. It just follows the mutual information being non-negative. Quantumly, it took a lot of sweat, and it was due to Lieb and Ruskay in the early 70s. And even interpreting the conditional mutual information is a pretty challenging thing. And so I've been pretty application-focused here, but I just want to mention one beautiful open problem in quantum information theory which might have relevance here, which is the problem of a quantum Markov state. So classically, if the conditional mutual information is exactly 0, then your system is in a Markov state. So P of A, B, C equals P of A, P of B given A, P of C given B, etc. That's equivalent to conditional mutual information being 0. Quantumly, there's a similar exact characterization when the conditional mutual information is 0. It's more complicated, but it exists, and I can tell you about it afterwards if you want. Classically, this characterization is robust. If the conditional mutual information is epsilon, then you're epsilon close to something of this form in relative entropy distance. Quantumly, that appears to be false. And if you want to talk about an approximate quantum Markov state, there are kind of many different possible definitions that you can think of, and they don't really appear to be equivalent without losing dimension factors. And on the one hand, that's perhaps an obscure question of quantum information theory. On the other hand, we're starting to get into a lot of tools that make use of conditional mutual information, and I think it would be a very useful thing in helping to analyze them. So returning to this, conditioning on a quantum system is problematic. And that is basically where the one LOCC restriction comes from. It says, if I just try to carry this out using quantum states, it's going to be really hairy. And if you ever tried to read the Brandau-Christandel-Yard paper, you'll see they carried out with quantum states. And they got this result, but it was very difficult. And in this middle paper here, Fernando and I proved that the algorithm works with a much simpler argument. And the argument basically is measure the Bob systems, but not Alice's. And do the measurements in such a way where you basically measure these, look at the measurement outcomes of these. I'm not saying this very well. Basically, you don't measure. You don't measure until you have to. You consider that you could have measured all the systems, but you still keep track of what the underlying quantum state is. And then you can talk about what the quantum state of these two is conditioned on these measurement outcomes, as well as on what the classical distribution would be if you would measure it. And I think nothing is super deep there. It's just you have to be careful about when things are quantum and when things are classical. And so what this lets you do is it lets you use these ideas that work in classical information theory in a setting where there's still some quantum stuff going on, but you can't push it too far. And in particular, you still have to have the restriction that you're only conditioning on classical things. But that's essentially why the argument works, that if you condition all these things, you get something that's nearly decoupled. And that, after all, is what separable is about. Separable says there's some classical variable out there. Once I condition on it, I'm nearly independent. And a further subtlety is you don't have to be independent in general. You just have to be independent with respect to this known measurement. But that's OK, because you just have to prove that it works. For each measurement, you have to prove that it works. And so that's what we do. So previously, people had proved.
Sorry, so what's that with SD?
OK, so what that proves is that k-extendable is a good approximation to separable. And so let me be a little bit more precise. Let me write here h sub k extendable of m is less than or equal to this quantity right here. OK? It's always greater than or equal to h sep, because k extendable strictly includes sep. But it's not too much bigger.
Yeah, and this epsilon has to do with k, so it's
That's right.
It's like log n of it.
That's right. And the better k you, and so so we know qualitatively that this hierarchy converges. So yeah, so just backing up a step, if I've lost you in the details, this hierarchy converges. The better k is, the bigger k is, the closer you are to separable. But you're looking at states of this many systems. So the dimension is n to the k plus 1. And the beautiful thing is these are general states. There's no separability condition. So you're just looking at density matrices. So you're looking at positive semi-definite operators with trace 1. So you just have to do a semi-definite program of this size. And great. So you have this hierarchy of semi-definite programs of k increasing. And as k increases, you get more and more accurate. Now so that's the easy part. And now the hard part is to say, how large does k have to be to get a desired approximation? And I guess there was a fair amount of quantum work on this before that didn't use information theory. And all that work found that k had to be like n over epsilon, which is, I think, nice from a physics point of view to know that, but worthless from an algorithmic perspective. And it was really the information theory that got k going like log n. And that's why after first trying simpler techniques, we ended up bringing in these information theoretic ones.
Wait, so you're saying that separable states is approximated by these k-extendable states for k equals log n.
And that's an SDP, yeah.
Why is that
OK, so an exact SDP. So rho tilde, what is rho tilde? Rho tilde belongs to d of n to the k plus 1. D of n is the set of density matrices. That's a semi-definite set.
Yeah, and you need to impose the conditions that ABIs are all identical.
And then I have a linear constraint. So linear constraint on a semi-definite set. Yeah, so this is the k-extendable condition. It says I've got my original rho AB, and that should equal all of the marginals of the extension. And the point about monogamy is that means they cannot be very entangled intuitively.
That's what the entropy.
And this makes it precise.
It's really some kind of proof of
Exactly.
monogamy.
Exactly. Yeah, and I should say monogamy, there's not like a theorem of monogamy. It's sort of a general principle, and you prove what you can, and this is a proof of a version of monogamy. So, all right, it's 12:35. I don't want to eat into your lunch too much. Let me just briefly, I think I've talked about open questions a good deal. So, of course, improving all of these results, you can see how it's sort of tantalizingly close in many places. And because of the quantum information perspective, there's questions. I've sort of tailored this as assuming that you care about unique games primarily, but of course, there are all these quantum information questions which are also nice. And so there might be things that aren't useful for algorithms but are still nice quantum information questions, like understanding the quantum conditional mutual information better, I think would be nice, even if it doesn't have applications, but it might have applications. And I'll mention also one improved version of this algorithm, which is, OK, one improvement you can make is force the bobs to be symmetric. And in practice, if you're going to implement this, you'll save k factorial dimensions. And you lose nothing, because if a k extension exists, its symmetrized form is also a k extension, so you might as well. But that doesn't appear to buy you very much. However, if you realize that, why are we working with matrices in the first place? The row and column indices, like why is a row index so different from a column index? You could imagine another kind of symmetry under swapping row and column indices. And that's called a transpose. When you swap the row index with the column index, that's a transpose. But you don't want to do it for all of them at once. You can think of this as you have k plus 1 row indices and k plus 1 column indices. If you just swap some of them, it's called a partial transpose. Right? You could have identity, tensor transpose. So you can talk about symmetry under partial transpose. And this is something that quantum information people have trouble with because it's not a physical operation. There's no, I can physically swap two systems. I cannot physically do the partial transpose. But it might dramatically improve the bounds. And so that, I think, is another natural place to look next. Can we extend either quantum information or other techniques to better understand this partial transpose? Is a nice area to look next. And I think, and there's one other thing. I never even mentioned Lasserre. But in fact, this hierarchy is Lasserre. is the Lasserre hierarchy. It's just another name for it. So if you want to know what that is, I've secretly been telling you about it the whole time. OK, thanks for your attention.
So, more questions besides
Just a quick thing. This is somewhat unrelated, but do you know if this H-sub view of the 2-to-4 norm is kind of in any way related to planet clique? I mean, you can always look at the 2-to-4 norm as like
Oh, right.
spectrum norm of four tensors.
Yeah, so there's a paper by Zampala and Charles Brubacher, that shows that planted clique can be reduced to a tensor problem over 3 index tensors. And in this paper, we show that that 3 index tensor problem is basically equivalent to H-sep. It's a very easy reduction. And so what they showed is that you could reduce, that clique is weaker than H-sep, or planted clique. And so that's pretty similar. And so you could say that was an evidence of hardness of H-sep. And then it was sort of, and then what we showed was 3 sat log squared n, which doesn't quite subsume this one, because
I mean, it's a special tensor in the case of the clique. It's not really, it's a random tensor.
well, with some planted entries, I guess. Yeah. Yeah, so I guess what you could do, but you're right, though, that does open up a new possibility, which is you could say, well, look at the tensors. We've been saying, look at the tensors you get from this, and they're kind of horrible and complicated. You could say, look at the tensors you get from this. Maybe they're nicer. We haven't done that.
Yeah, I mean, maybe there's some quantum-y kind of interpretation of the tensors we're getting from planet clique and maybe H-sub.
Yeah, no, that's a good idea, actually. That's a good idea.